Welcome, students. Here I am, back with my nephew.
I'm Joey.
Hey, Joe. We're going to do video 3.4, part D on intermolecular forces. Hey, Joe, by the end of this video, you know what? You should probably know something about intermolecular forces.
I'm hoping.
Yeah, and you probably should be able to tell me how strong they are.
Okay.
Based on their structure and based on a couple other things. So why don't we get started? So let's talk about states of matter. Before we answer this question, Joe, what makes this a solid, I think it's important to realize that molecules are always moving. These spheres aren't just stationary, they're always wiggling back and forth. Okay, so they're always kind of going back and forth. So how do we know this? We know this because of something called temperature. Temperature is really just the measurement of how fast molecules are moving. The faster they move, the
higher the temperature.
Right, exactly right. So it's only at absolute zero, the coldest possible point, that molecules stop moving. Okay? Any other point, molecules are moving at least slightly. Okay? So these particles in a solid here are moving, even though they're kind of stacked and close together. They're kind of shaking in place, shimmy shaking, okay? But the answer to the question, what makes that a solid, is not that they are close together. It's the fact that those spheres, those particles, are sticking together. They're attracted to each other. And that attraction, that glue that's holding them together, is stronger than the motion that's trying to pull them apart. Does that make sense?
It makes sense.
Okay. So now if we look at a gas, like we have down here, this guy here is a gas. So now we should be able to take that opposite logic and apply it to this. These are gas particles, and we know that gas particles are zipping around in all sorts of directions. Okay? And how do we know gas particles are moving?
Because the temperature.
Right, because they have a temperature, right? So as long as they have a temperature, they're moving. But if they're moving independently from each other, that means whatever's holding them together isn't very sticky. So that's what you're calling intermolecular forces, is the stickiness or the thing that is holding the molecules together. If it's strong, that's going to give it a certain property. If that stickiness or force is weak, it's going to give it a different property. Okay. So solids have strong intermolecular forces.
And gases don't?
And gases don't. Okay. So let's move forward here. So there are actually 5 types of intermolecular forces. And I will tell you, Joe, that intermolecular forces is just like everything else that we've done in chemistry. It's all about positives and negatives coming together. Opposites attract. I don't know if you know that song or not, but
not really.
No. Okay, but so basically, if you find the positive and you find the negative, then you can rate how strong the intermolecular force is, whether it's going to have a ton of glue or not a lot of glue. And so the 5 types of forces are and this is in order of strength. The strongest is ion-ion, and then the next is ion-dipole, hydrogen bonding, dipole-dipole, and London dispersion forces. Now I'm going to briefly overview each of these in this video. And then what I have is I'm going to have a video about each one specifically, and we're going to go into a lot of detail about each one of these 5 forces. Okay? But I do want to say that I'm going to present these a little bit out of order. I'm actually going to do number 4 first. Before I do number 3. Do you have any idea why, Joe?
All I know is number 3 is stronger than number 4.
Right. That's all you should know. So the reason why is because number 3 is a specialized type of number 4. So we have to know what a dipole-dipole is before we know anything about hydrogen bonding. Okay. So we're actually going to go through 1, 2, 4, 3, 5, but we're still going to get through them all. Okay. So let's first talk about ion-ion. Okay. Ion-ion forces are the strongest type of intermolecular force. Now, ion-ion forces are strong because the positive and the negative are very strongly attracted to each other. Okay? What we're looking for is the positive and negative, right? That's what I said. That's the intermolecular force. So a sodium ion has a positive charge.
Okay.
And a chlorine ion has a negative charge. And this happens because sodium, its one electron, is given to chlorine and therefore transfers electrons. So that means that this positive charge and this negative charge are permanently part of that ion. So because it's a permanent, how do you spell permanent? Whatever. If I scribble it, nobody will be able to get it. It's a permanent charge. Therefore, this charge is very strong, and this charge is very strong. This is a
positive,
and this is a
negative.
So what do?
So they attract.
And so the glue that holds that together
Very strong.
is going to be very strong. Okay, so now the next type of charges. Now this is called ion dipole. Now, in order for us to understand this type, we first have to understand what this word dipole means. A dipole just means that the molecule has a partial positive and a partial negative side. It has what we call a dipole moment. So here we have water, which is the most common compound to be polar. Now, water has a dipole. If we split this molecule in half, you can see that there is a partially positive side and a partially negative side. But those charges aren't permanent.
They're just partial.
They're just partial.
Okay.
They're not always there, because the electrons in these, as my students know, are always kind of moving around. Okay? So they're kind of around oxygen a lot, around hydrogen a little, but they're still just a partial charge. That's what that little symbol means.
Okay.
It's a partial charge. But then if I take this and I mix this with a sodium ion, what is the charge of a sodium ion?
Positive.
Positive. And what do positives like?
Positives like to attract
What do they like to attract?
to the negatives.
Negatives. So we have a positive attracting a negative. So there is an attraction there. But it's between a permanent charge
And a partial.
and a
negative.
partial charge, right?
Okay.
So this isn't as strong as two permanent charges attracting each other.
So it's the second strongest.
So it's the second strongest. Now, this only occurs, Joe, when you're dealing with something dissolving. So if you have sodium chloride, salt water, dissolving, that's what's happening here. Okay? It's not for anything else. So that's a hint to all my students that this only happens in very limited cases. Okay? So now, let's say we had a chloride. Let's do the other part of this. What's the charge on a chloride ion?
It's a negative.
It's a negative. What do negatives like?
Negatives like to attract to the positives.
Right. And is there a positive side here?
Yes.
Yeah. So you can see that if we started off with sodium chloride, which attract each other, it's possible that these two things attract each other too. The positive of this attracts to the partial negative, and the negative here attracts to the partial positive. More on that in a video about ion dipole forces, but you get the idea. Okay, next. So now remember we had to skip. So now we're talking about dipole forces. So here we have ammonium, it's not ammonium, it's nitrogen trifluoride. Okay, nitrogen trifluoride is a very interesting molecule, and this is polar. Okay, what I'm going to do is I'm going to bring one of these down here so that you can see its polarity. Just like when we were talking about dipoles, here we have a partial positive. And around the outside of it, we have a partial negative. So partial positives are attracted to
The partial negatives.
partial negatives. And so what we have here is, if we take this guy, which atom, Joe, is the positive atom in this ammonium, or this nitrogen trifluoride?
The N?
The N. So that's going to be looking for the negative, right? So yet this side of this molecule is attracted to this molecule.
Okay.
Okay. Now, what about this molecule? Where's Where's the what are the negative atoms in this molecule?
The negatives are the F's.
The F's. So guess what the F's are going to be attracted to here?
The S is in the other one.
To the
Oh, that's not an S.
that's an N there.
N.
Okay? And so now we can add more. And so the fluorine, the partial negative on the fluorine, is going to be attracted to the partial positive on the nitrogen. And then we can add more and more and more, and these things can get bigger and bigger and bigger. And so when we have a million molecules, this is what brings a million molecules together and makes them a liquid or a solid, is the strength of the intermolecular forces. If you have a weak intermolecular forces, they're all just going to fall apart and not stick together. And so you'd have a gas. Okay? So again, more on this later. So now dipole is important for us to talk about, but kind of the most common force here is hydrogen bonding. And you can see that water, this is water, has a dipole. And so the dipole, this is a partial negative, so what is that attracted to?
A partial positive.
Partial positive? Do we have partial positive here in this other thing?
No, we don't. Oh, yeah, we do, right there at the bottom.
Yeah, right there at the bottom. There it is, right there, right? Okay, so that partial positive is attracted to the
partial negative.
So this guy is attracted here, and so there's an attraction there. But the reason why it's special is because a hydrogen bond is stronger. So when hydrogen is involved in the dipole, okay, that makes it stronger than a normal dipole.
Oh, okay.
So going back here, a normal dipole is what we have here, dipole, but the only difference is we have hydrogens in it. Okay.
So the hydrogen's making it stronger.
Making it stronger because it's smaller.
Okay.
So that there's things. Again, we'll talk a little bit more about that. But hydrogen, in order for it to hydrogen bond, has to bond to nitrogen, oxygen, or fluorine. It's the only way that there'll be a hydrogen bond. So as we see in this molecule, we have hydrogen, and what is it bonded to?
To the oxygen?
Oxygen, yeah, so it's a hydrogen bond, right? Okay. If hydrogen were not bonded to that, it wouldn't look that way. But now if we bring in more molecules, you can see that just like we did with the NF3, we can have these all attracted to each other, and you can have all sorts of things going on.
So the hydrogens and the oxygens are all sticking together.
Right, they're all sticking together, which is why water is a liquid, because they're sticking together. Okay, but they're not sticking together as strongly like ion. They're not. It's not a permanent charge.
Partial.
It's just a partial charge. Okay. So then the last one is called London dispersion forces. London dispersion forces are the weakest, and they exist in every molecule or particle known to man. And this is the weakest because when something doesn't have a polarity, okay, all we're looking at here is the nucleus of an atom. And what's the charge in a nucleus of an atom? Positive. And then the electrons are floating around the outside and they're negatives. And so what this is the attraction between the nucleus of one to the electrons of another. So that is a very weak force. And so this is why gases stick together a little bit and then they come together maybe to form a liquid at really low temperatures because the motion is really slow or something like that. Okay. So let's go on here. We'll actually try some of these yourself. So there's a table of electronegativity values to determine if something has polar bonds and whatnot. But if you want, you can pause the video and then try these yourself. So I assumed you paused the video out there, but so Joe, do you think you can maybe do some of this stuff?
I can give it a try.
You can give it a try. So this guy here is ammonia. So what do you think ammonia's intermolecular forces are?
Is it a hydrogen bond?
It is a hydrogen bond. Do you know why?
It's because it's a dipole.
Right.
And it has London dispersion forces?
It also has London dispersion forces, but let's go back here. Why is it a dipole?
Because it's hydrogen and nitrogen.
It has hydrogen bonded to a nitrogen, right? Okay, so now what about here? RBBr, what is that one?
So that's an ion.
It's an ion, okay, because it's a metal bonded to a non-metal.
Okay.
And then what else is also
that's
present?
That's also London dispersion forces.
Okay, and then what about SF4?
That is a dipole.
And then the last one is
It's just London dispersion forces.
that's right.